السلام عليكم ورحمة الله وبركاته. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Here we have the lecture on the exchange of gases in the respiratory physiology section of the respiratory block. You all know that oxygen is essential for our survival. We need oxygen to generate most of the energy which is required by our cells to function properly. We call the process or the processes of supplying oxygen to the metabolizing tissues of our body and removing carbon dioxide respiration. Man, being a complex and multicellular organism, respiration in man is not a simple process. Rather, respiration involves a series of integrated sequential processes or steps. The first step in respiration in humans is pulmonary ventilation. And by pulmonary ventilation, we mean the inflow of air during inspiration and the outflow of air during expiration. In other words, we mean the breathing movements of inspiration and expiration. So, pulmonary ventilation is equivalent to breathing, but is not equivalent to respiration, because respiration is the entire process till oxygen is supplied to the cells of our body and carbon dioxide is removed from the cells and eliminated into the external environment. The second step in respiration is the exchange of respiratory gases in the lungs between the air in the alveoli and the blood in the pulmonary capillaries. This takes place by diffusion across what we call the respiratory membrane or the alveolo-capillary membrane or the alveolar membrane. This membrane is composed of the wall of the alveoli and the wall of the pulmonary capillaries, because the pulmonary capillaries surround the alveoli. This membrane is composed of several layers, as we will see in the next slide. However, it is very, very thin, and this helps and favors the diffusion of oxygen and carbon dioxide. It is approximately 1 micrometer or 1 micron thickness. By 1 micron or 1 micrometer, we mean 1 multiplied by 10 to the power of -6 of a meter. So if 1 meter is divided into million parts, each part of these million parts is known as a micron or a micrometer. However, the surface area of such respiratory membrane or alveolo-capillary membrane is huge, because you have large number of alveoli. The surface area is approximately the area of a tennis court, which is approximately 75 meters square. After exchange of respiratory gases across the respiratory membrane, we have the third stage of respiration in man, which is the transport of oxygen and carbon dioxide. So oxygen is transported from the lungs to the heart, then from the left side of the heart to the cells of the body, where we have another exchange process of gases. So the metabolizing tissues take up oxygen from the blood that flows along the systemic capillaries, and they use oxygen to generate adenosine triphosphate, the energy. And while energy is being produced, carbon dioxide is also produced as a byproduct of metabolism. So we have diffusion of carbon dioxide from the metabolizing tissues to the interstitial fluid and then to the systemic capillaries. And now the blood becomes venous blood or mixed venous blood or deoxygenated blood. Okay, so this blood is low in oxygen and high in carbon dioxide, is transported to the right side of the heart, then from the right side of the heart again to the lungs for reoxygenation. The last stage of respiration of man is the internal respiration, and this takes place within the cells of the body themselves. Where in the cells? Within the mitochondria, as you all know. You have covered the first step, which is pulmonary ventilation, in the previous lectures, and in this lecture we shall focus on the second stage of respiration, which is the exchange of gases in the lungs. The last step, which is internal respiration, this is dealt with in biochemistry. So here we have the layers of the respiratory membrane, which is composed of the wall of the pulmonary capillaries, the endothelial cells, and the basement membrane. Then we have the interstitial space between the wall of the capillaries and the wall of the alveoli. The wall of the alveoli is composed of a thin fluid or water layer with the pulmonary surfactant. Then we have the alveolar epithelial cells, which we call them the pneumocytes, and there are two types of pneumocytes, type 1 pneumocytes and type 2 pneumocytes, and they rest on a basement membrane. So these are the layers which oxygen should cross in order to diffuse from the alveolar air to reach the blood in the pulmonary capillaries, and they are the same layers which carbon dioxide should diffuse in the opposite direction. The thickness of these layers is very, very small, as I mentioned in the previous slide. It is approximately 1 or even less than 1 micron or micrometer. So now, what forces oxygen to diffuse from the alveolar air into the blood in the pulmonary capillaries, and carbon dioxide diffuses in the opposite direction? We need a force to move oxygen and to move carbon dioxide. This force is in the form of a pressure gradient. So oxygen moves from the alveolar air into the blood in the pulmonary capillaries because the partial pressure of oxygen in the alveolar air is higher than the partial pressure of oxygen in the blood in the pulmonary capillaries. The opposite is true for carbon dioxide. So it's true to say the opposite for carbon dioxide. So let's talk what is meant by partial pressure. And in order to understand the concept of the partial pressure, الضغط الجزئي, we need to talk about an important law in chemistry and physics, which is the Dalton's law, قانون Dalton. Dalton's law states that the pressure exerted by each gas in a mixture of gases, for example, the atmosphere is the layer of gases which surround Earth. This layer is composed of a mixture of gases. We have oxygen in the atmosphere, we have nitrogen, we have carbon dioxide, we have helium, and we have other inert gases. Because these gases have weight, so the atmospheric layer exerts pressure on the surface of Earth. This pressure, which is exerted by the atmosphere, is known as the atmospheric pressure, or is known as the total atmospheric pressure. How much is this total atmospheric pressure when air is dry and at the sea level? Air is dry, we mean that there are no water vapor in air, al-hawa al-jaf, like the one which we have in Riyadh or in Qasim. عند مستوى البحر, and in dry air the atmospheric pressure is 760 millimeters of mercury. What is the meaning of this? So if we have a container of mercury and we have an inverted tube, this atmospheric pressure would exert a pressure, a force on the surface of mercury, and the mercury would rise in the inverted tube up to 760 millimeters of mercury. This is the way we measure the atmospheric pressure, by the manometer. Now, the partial pressure exerted by each gas in the atmosphere is related or is dependent on the fractional concentration of gas in the atmosphere. So if the fractional concentration of nitrogen is 79%, this means that 79% من الtotal pressure is exerted by nitrogen. So the partial pressure of nitrogen, الوضعات الجزء للنيتروجين, is equivalent to 760 millimeter of mercury, the total pressure, multiplied by the fractional concentration of nitrogen, which is 600 millimeters of mercury. The fractional concentration of oxygen in dry air at the sea level is 21%. So the partial pressure exerted by oxygen in the atmosphere, which is dry and at the sea level, is equivalent to 760 millimeters of mercury multiplied by 21%, via 0.02, and so the partial pressure of oxygen is 160 millimeters of mercury. Okay, when the atmosphere is humid, i.e., there is water vapor in the atmosphere, now the picture is different. Now the water molecules exert a partial pressure. When the atmosphere is fully saturated, or when air is fully saturated with water vapor, the partial pressure exerted by the water molecules is equivalent to 47 millimeters of mercury at 37 degrees centigrade. So now the partial pressure of water vapor is part of the total pressure. So if we live in Riyadh or in Qasim, we inspire dry air, where the partial pressure of oxygen is 160 millimeters of mercury. However, this dry air is irritant to the alveoli. So what should happen to this dry air? As this dry air flows along the conducting zone of the respiratory system, the conducting zone begins with the nose and ends with the terminal bronchioles, air gets humidified, air gets fully saturated with water vapor. So the pressure of the water vapor in the conducting zone is 47 millimeters of mercury. So now the remaining pressure is 760 minus 47 millimeters of mercury. And this should be taken into consideration while calculating the partial pressure of oxygen and the partial pressure of carbon dioxide in the conducting zone of the respiratory system. Now, we need to know that the total atmospheric pressure may get changed. For example, as we ascend at high altitudes, the atmospheric pressure decreases, while the atmospheric pressure increases with depth underwater. Also, we have chambers which could be hypobaric with low pressure or hyperbaric with high pressure. The change in the total atmospheric pressure will not affect the partial pressure of the water vapor as long as the temperature remains constant. So water vapor pressure is not affected by the total pressure. So now let's see what are the partial pressures of oxygen, carbon dioxide, okay, in dry air at the sea level, and in the conducting zone, and in the alveoli, and in the arterial blood. This is the blood which leaves the lung and goes to the left side of the heart and then goes to the tissues. And in the venous blood, this is the blood which leaves the tissues after the tissues have taken oxygen and added carbon dioxide to the blood. And the partial pressures of these two important gases in the interstitial fluid or interstitial space and within the cells. We mentioned the partial pressure of oxygen and carbon dioxide in dry air at the sea level. Oxygen, 160 millimeters of mercury. Carbon dioxide, the partial pressure, ضغط الجزء الكربون dioxide is negligible, almost zero. In the conducting zone of the respiratory tract, now water vapor is added, and the partial pressure of water vapor is now 47 millimeters of mercury. So we need to take this into consideration while calculating the partial pressures of oxygen and carbon dioxide. So the partial pressure of oxygen now in the conducting zone is not 160 millimeters of mercury, rather it is 145 millimeters of mercury. In the alveolar air, the A means alveolar air. Partial pressure of oxygen is 102 millimeters of mercury approximately, and the partial pressure of carbon dioxide in alveolar air is 40 millimeters of mercury, because now carbon dioxide has diffused from the blood in the pulmonary capillaries into the alveolar air. Now, in the blood, which is going to the tissues of the body, along the arteries, we call it the arterial blood, the partial pressure of oxygen is 95 millimeters of mercury. Says it is slightly less than the partial pressure of oxygen which we have in the alveolar air. And the partial pressure of carbon dioxide is 40 millimeters of mercury. In the venous blood, this is the blood which leaves the tissues. V means venous. The partial pressure of oxygen, 40 millimeters of mercury, because the tissues have taken oxygen. And the partial pressure of carbon dioxide is 45 or 46 millimeters of mercury, because the tissues have added carbon dioxide to the venous blood. In the interstitial space or interstitial fluid, which surrounds the cells of the body, the partial pressure of oxygen is 40, that of carbon dioxide is 45, and within the cells, the partial pressure of oxygen is 20, and that of carbon dioxide is 46. So this figure summarizes what we have just mentioned. So this is the inspired air when it is dry and at the sea level. Partial pressure of oxygen 160 millimeters of mercury. Partial pressure of carbon dioxide is negligible. It's approximately 0.3 millimeters of mercury. In the alveoli, this is not the picture. The partial pressure of oxygen is 102 or 104 millimeters of mercury, and the partial pressure of carbon dioxide is 40 millimeters of mercury. This is the venous blood. This is the mixed venous blood, which returns from the tissues to the right side of the heart and then to the lungs. Partial pressure of oxygen is 40, that of carbon dioxide is 45 or 46 millimeters of mercury. Now, because there are pressure gradients for oxygen and carbon dioxide, so we have diffusion of oxygen from the alveolar air into the blood in the pulmonary capillaries, and we have diffusion of carbon dioxide in the opposite direction. So the partial pressure of oxygen now becomes 104 or 102 millimeters of mercury, and that of carbon dioxide is 40. Now this blood goes through the pulmonary veins to the left side of the heart. Now what you have noticed is that the partial pressure of carbon dioxide is the same as the partial pressure of carbon dioxide in the blood which has just left the lungs. However, the partial pressure of oxygen in the arterial blood has dropped a bit. It was 104 or 105, now it is 95 millimeters of mercury. And we will explain this in the subsequent slides. This is the partial pressures of oxygen and carbon dioxide in the interstitial fluid. Now, this is the partial pressure of oxygen and carbon dioxide in the venous blood. So, same thing here. So, this is in the atmospheric air, partial in the atmospheric air. assuming that the atmosphere is dry and at the sea level, the partial pressure of oxygen is 160 millimeters of mercury. That of carbon dioxide is negligible, approximately 0.3 millimeters of mercury. In the alveolar air, partial pressure of oxygen is approximately 100 or 102 or 104 or 105. Okay, we have different values in different books. Okay, and that of carbon dioxide is 40 millimeters of mercury. So this is what we have in the blood returning to the left side of the heart in the pulmonary veins. And this is the picture which we have in the systemic arteries, then the cells, then in the systemic veins. And now this is the same blood which flows through the systemic veins back to the right atrium, then to the right ventricle. It is the same blood which flows along the pulmonary arteries. So the partial pressure of oxygen and partial pressure of carbon dioxide is essentially the same. Now, we have finished with Dalton's law, and we have known the importance of Dalton's law, that there are partial pressures of oxygen and we have partial pressures for carbon dioxide. And there are pressure gradients for oxygen and for carbon dioxide. We have another important law in physiology or in biophysics, which is known as the Fick's law of diffusion. This Fick's law of diffusion states that the volume of gas X, it could be oxygen, it could be carbon dioxide, transferred per unit time, we call this is the diffusion rate. This is directly proportional to the pressure gradient. So the higher the pressure gradient, the larger is the diffusion rate. It is also directly proportional to the surface area of the membrane across which the gas diffuses. And it is also directly proportional to D. What's D? This is a diffusion coefficient of the gas through the membrane. But it is inversely proportional to delta X. Delta X, this is the distance, or this is the thickness of the membrane through which the gas diffuses. So now let's apply Fick's law of diffusion to the diffusion or to the exchange of gases across the alveolo-capillary membrane. So now oxygen diffuses from the alveolar air into the blood in the pulmonary capillaries, because the pressure of oxygen is higher in the alveolar air. We mentioned that it is 100 or 102 or 104 and 5, so it is from 100 to 105 millimeters of mercury. Carbon dioxide diffuses in the opposite direction. Why? Because the partial pressure of carbon dioxide here in the blood in the pulmonary capillaries is 45 to 46 millimeters of mercury, while it is only 40 here. Okay? So now let's describe again the diffusion gradients for oxygen and carbon dioxide in more details. So we mentioned that oxygen diffuses from the alveolar air to the arterial end of the pulmonary capillary. The arterial end of the pulmonary capillary is this end, where we have deoxygenated blood, because we have here the pulmonary artery. The pulmonary artery divides into smaller branches. Then we have the pulmonary arterioles. Then we have the pulmonary capillaries. So the partial pressure of oxygen in the alveolar air is 100 to 105 millimeters of mercury, and at the arterial end of the pulmonary capillary it is approximately 40. So there is a gradient for oxygen, and it is because of this gradient oxygen diffuses and it equilibrates. Now the partial pressure of oxygen equilibrates to approximately 100 to 105 by the end of the pulmonary capillaries, i.e. at the venous end of the pulmonary capillaries. Now a very important question arises. This is what we mentioned here in this slide. We mentioned here that here the partial pressure of oxygen is from 100 to 105 millimeters of mercury, while in the blood, which is now going to the left atrium and then going to the tissues, the partial pressure of oxygen is 95. So there is a decrease. There is the partial pressure of oxygen is decreased a bit. What are the reasons for this partial drop in the partial pressure of oxygen? This is because of what is known as the physiological shunt. What is the meaning of the physiological shunt? By physiological shunt, we mean the venous admixture. What is the meaning of venous admixture? This is the mixing of the oxygenated blood with non-oxygenated blood. Oh, what's the meaning of this? So this oxygenated blood, where the partial pressure of oxygen was 105 or 104 millimeters of mercury, is mixed somehow with deoxygenated blood. And it is because of this mixing, the partial pressure of oxygen is now 95 millimeters of mercury. And this is the partial pressure of oxygen which goes to the tissues. So what is the source of this deoxygenated blood? The physiological shunt or the venous admixture is the cause. And we have two types of shunts. We have right to left anatomic shunt and we have the alveolar shunt. What is the meaning of right to left anatomic shunt? The meaning of right to left anatomic shunt is that there is venous blood from part of the systemic circulation which drains into the pulmonary veins. This part of the systemic circulation is known as the bronchial circulation. So remember, in the lungs, we have two circulations. The main one is the pulmonary circulation. But also the airways, they need oxygenated blood. They take oxygen and they add carbon dioxide. So we need blood supply to the conduction or to the conducting zone of the respiratory system. And this is not pulmonary circulation. This is part of the systemic circulation. Now, the venous blood, which returns from the conducting zone, it doesn't go to the right atrium as the venous blood from other parts of the body. Rather, it drains into the pulmonary veins. Also, the Thebesian veins. These are veins present in the myocardium. They drain directly into the left atrium and left ventricle. So this is what we call right to left anatomic shunt. Okay, what about the alveolar shunt? Okay, now, under normal conditions, we have a small alveolar shunt. And this is because of the regional differences in blood flow and ventilation. We will describe this in one complete lecture. So at the base or at the bottom of the lung, ventilation is less than blood flow. Accordingly, not all of the blood which goes through the pulmonary capillaries at the base of the lung gets oxygenated. So in this case, the blood passes some of the alveoli but is not oxygenated. So normally we have a very small physiological shunt, but in pathological conditions like pneumonia, like pulmonary edema, like atelectasis, the alveolar shunt becomes marked. So approximately, we mentioned 2% of the cardiac output bypasses the alveoli. And we mentioned that these 2% of the cardiac output, they do not get oxygenated. Why? Because somehow they bypass the alveoli. How do they bypass the alveoli? Is either by the right to left anatomic shunt, because the bronchial veins drain directly into the pulmonary veins, and the Thebesian veins from the coronary circulation drain directly into the left atrium, left ventricle, or because of the very small amount of the alveolar shunt. So accordingly, there is a very little difference between the partial pressure of oxygen in the alveolar air, we call it A capital, and in the arterial blood, which we call it A small. This difference is normally approximately 5 to 15 millimeters of mercury. If the difference is large, this indicates abnormal right to left anatomic shunt, like what we have in ventricular septal defects, or there could be impaired exchange of gases across the alveolar capillary membrane, like what we have here in pneumonia, pulmonary edema, and atelectasis, collapse of the alveoli, or it could be due to the low regional ventilation to perfusion ratio at the base of the lung, and we will discuss this in one complete lecture, as I've just mentioned. So this diagram summarizes the right to left anatomic shunt. So this is the bronchial veins. This is part of the systemic circulation. They drain directly into the pulmonary veins. So at the level of the tissues, there is a diffusion gradient for oxygen and also for carbon dioxide. Oxygen diffuses from the arterial end of the systemic capillaries to the interstitial space. Then oxygen diffuses from the interstitial space into the cells, because there is pressure gradient for oxygen between the blood and the systemic capillaries and the interstitial space. Then there is a pressure gradient of oxygen between the interstitial space and the cells. Carbon dioxide diffuses in the opposite direction. So carbon dioxide diffuses from the cells, then to the interstitial space, then from the interstitial space to the blood in the systemic capillaries. So the partial pressure of carbon dioxide in the cells is approximately 46 millimeters of mercury, because carbon dioxide is produced in the cells during aerobic cellular respiration when adenosine triphosphate is being formed. The partial pressure of carbon dioxide in the interstitial space is approximately 45 millimeters of mercury. So still, there is a pressure gradient for carbon dioxide. And it is because of this pressure gradient, carbon dioxide now diffuses from the cells to the interstitial space. Then carbon dioxide diffuses from the interstitial space to the arterial end of the systemic capillaries, because again there is a pressure gradient for carbon dioxide. Then lastly, carbon dioxide diffuses. You can see here, blood goes to the right atrium, to the right ventricle, to the pulmonary artery, then to the pulmonary capillaries. So the partial pressure of carbon dioxide at the arterial end of the pulmonary capillaries is approximately 45 to 46 millimeters of mercury, and we mentioned this early in the previous slides. The partial pressure of carbon dioxide in the alveolar air is only 40 millimeters of mercury. So carbon dioxide now at the level of the lungs diffuses in the opposite direction to the direction of oxygen diffusion. So it diffuses from the blood in the pulmonary capillaries to the air in the alveoli. So this figure summarizes what we have just mentioned. So oxygen moves due to pressure gradient from the alveolar air to the blood in the pulmonary capillaries, and carbon dioxide moves in the opposite direction because of the pressure gradient. And remember, here we have two shunts. These two shunts are the right to left anatomic shunt, and we have the physiological shunt. And it is because of the sum of these, the sum of the alveolar shunt and the right to left anatomic shunt, we call it the physiological shunt. Because of this physiological shunt, now the partial pressure of oxygen in the arterial blood is 95 millimeters of mercury. That of carbon dioxide remains the same, 40 millimeters of mercury. So now let's talk about a very important physiological concept related to the exchange of gases. And this concept is what we call the diffusion limited and the perfusion limited gas exchange. The exchange of gases across the respiratory membrane from the physiological point of view is described either limited by diffusion, it could be either limited by diffusion or limited by perfusion. What's the meaning of this? Diffusion limited gas exchange means that the total amount of the gas which is transported across the alveolar capillary membrane is limited by the diffusion process. So in this case, the partial pressure gradient for the gas is maintained. And what maintains the partial pressure gradient of the gas? This is because the gas doesn't get equilibrated with the partial pressure in the alveoli. So there is no equilibration between the alveoli and the pulmonary capillaries. So the partial pressure gradient exists. And as long as this partial pressure gradient for the gas exists, the gas keeps on diffusing. And now what determines the diffusion of the gas is the diffusion process itself. So had the pulmonary capillaries being longer, the gas would continue to diffuse because the partial pressure gradient is still there. The second type of diffusion of gases across the alveolar capillary membrane is what we call the perfusion limited gas exchange. Perfusion يعني الانسياب الدموي across the pulmonary capillaries. The perfusion limited gas exchange means that the total amount of the gas which is transported across the alveolar capillary membrane is limited by perfusion, is limited by the blood flow through the pulmonary capillaries. In such case, the partial pressure gradient is not maintained. Why? Because the gas gets equilibrated between the alveoli and the pulmonary capillaries. So diffusion stops because there is no more pressure gradient. Why? Because the gas equilibrates somewhere along the pulmonary capillaries. So now the only way to increase the amount of the gas which is transported across the respiratory membrane is to increase the pulmonary blood flow. And this is clear here in this diagram. So on the x-axis we have the length along the pulmonary capillaries, and on the y-axis we have the partial pressure of the gas in the pulmonary capillaries. So the solid red line, this is the solid red line, This shows the partial pressure of the gas in this is the solid red line here in case A, and this is the solid red line here in case B. This is the partial pressure of the gas in the pulmonary capillary blood. Now, the dashed green line across the top, this is the partial pressure of the gas in the alveolar air. And this doesn't change. As you can see, it doesn't change. It remains constant. Now, the dashed pink area, this gives the partial pressure gradient between the alveolar gas and the pulmonary capillary blood along the length of the pulmonary capillary. Okay, here in case A, you can see that there is pressure gradient for that gas, and this pressure gradient is maintained along the length of the pulmonary capillary. The gas doesn't get equilibrated between the air in the alveoli and the blood in the pulmonary capillaries. So in this case, the total amount of the gas transported across the respiratory membrane is diffusion limited. So the gas keeps on diffusing along the length of the pulmonary capillary. And as I mentioned, had the pulmonary capillary to be longer, the gas would continue to diffuse. لو البلمونري كابيلاري كانت أطول الجاز هيستمر في الديفيوجن. ليه؟ لأن الجاز doesn't get equilibrated between the alveolar air and the blood in the pulmonary capillaries. This is not the case here. For that gas, which could be the nitric oxide or oxygen. For that gas, okay, now the partial pressure of the gas increases and reaches now the partial pressure of the gas in the alveolar air. So now the partial pressure of that gas in the alveoli is equal to the partial pressure of the gas in the blood in the pulmonary capillaries. And this is reached at a particular length along the pulmonary capillary. So at this length, there is no more pressure gradient for that gas, because the gas gets equilibrated between the alveolar air and the blood in the pulmonary capillaries. So now the partial pressure of that gas in the blood in the pulmonary capillaries is equivalent to the partial pressure of the gas in the alveolar air. So there is no more pressure gradient to push this blood across the alveolo-capillary membrane. So the only way now to increase the amount of the gas which diffuses across, or which is transported across the respiratory membrane, is to increase the perfusion. So case A is diffusion limited gas, and case B is perfusion limited gas. So the oxygen is what? Do you think oxygen is diffusion limited gas or perfusion limited gas? Now forget about the red gas. Oxygen is the blue gas. And forget about the abnormal situation. We are talking about the normal situation. So again, this is the time or the length of the pulmonary capillary. And this is the partial pressure of the gas in the blood in the pulmonary capillaries. And at the top, this is the partial pressure of the gas in the alveolar air. So you can see here that oxygen takes approximately 0.25 seconds along the pulmonary capillaries, and its partial pressure now by this time is equivalent to the partial pressure of oxygen in the alveolar air. So now at this time the partial pressure gradient for oxygen is abolished. There is no more partial pressure gradient for oxygen. So the diffusion stops. You can see here, as you can see here. So the only way now to increase the amount of oxygen transported across the respiratory membrane is by increasing perfusion. So this is the oxygen is described as perfusion limited gas exchange. This is under normal conditions. However, under abnormal conditions or during strenuous exercise, the oxygen, the exchange of oxygen becomes diffusion limited. So same thing here. So this gas, by the way, the one in red, this is nitric oxide. And also the diffusion of nitric oxide across the respiratory membrane is also perfusion limited. Why? Because nitric oxide might even take lesser time than oxygen to get equilibrated between the blood in the pulmonary capillaries and the air in the alveoli. So it is perfusion limited. So this is same thing we have just mentioned here. So remember, during strenuous exercise, the exchange of oxygen becomes diffusion limited. So again, here we have a gas, and you can see here, this is the partial pressure of the gas in the blood in the pulmonary capillaries, and this is the partial pressure of the gas in the alveolar air. So you can see here that the partial pressure of the gas in the blood in the pulmonary capillaries, even by the end of the pulmonary capillaries, it doesn't reach the partial pressure of the gas in the alveolar air. So there is always a pressure gradient for this gas. And an example of this gas is carbon monoxide. So carbon monoxide doesn't equilibrate by the end of the pulmonary capillaries. And in fact, had the pulmonary capillaries been longer, the carbon monoxide would continue to diffuse indefinitely or until equilibration occurs. Again, the transport of oxygen across the respiratory membrane during strenuous exercise and in pathological conditions like emphysema and fibrosis is also diffusion limited. It's not perfusion limited. Okay? So this is what we have just mentioned here. So carbon monoxide in the alveoli is constant. It doesn't change the partial pressure of carbon monoxide. And along the length of the pulmonary capillary, carbon monoxide keeps on diffusing. But the partial pressure of carbon monoxide rises only very slightly. Why? Because carbon monoxide binds very strongly to hemoglobin. So its partial pressure in the plasma, it doesn't rise much. It rises only very slightly. So even by the end of the pulmonary capillary, the partial pressure of carbon dioxide would have not reached the partial pressure of carbon monoxide in the alveolar air. So carbon monoxide would continue to diffuse across the respiratory membrane had the pulmonary capillaries been longer, which is not it. So its exchange or its transport across the respiratory membrane is described as being diffusion limited. So this is the diffusion limited gas exchange for carbon monoxide. So still, the partial pressure of carbon monoxide is much less than the partial pressure of carbon monoxide in the alveolar air. Now, this is the transport of oxygen. Again, I'm repeating this. This is the transport of oxygen across the respiratory membrane, and the exchange or the transport of oxygen across the respiratory membrane is described as perfusion limited. However, this is the norm. It is perfusion limited. And we mentioned in the previous slides that it takes oxygen approximately 0.25 of a second to get equilibrated between the blood in the pulmonary capillaries and the air in the alveoli. So equilibration of oxygen occurs about 1/3 the distance along the pulmonary capillaries. And at this point, which is 1/3 of the length of the pulmonary capillaries, or at 0.25 seconds, the pressure, the partial pressure of oxygen in the pulmonary blood is exactly the same as the partial pressure of oxygen in the alveolar air, so there is no more pressure gradient for oxygen. So there is no more movement of oxygen across the respiratory membrane. And the only way to increase the total amount of oxygen transported is by increasing the perfusion. Under abnormal conditions, like what we have in emphysema or in fibrosis, and also during strenuous exercise, oxygen movement becomes diffusion limited, because even by the end of the pulmonary capillaries, the partial pressure of oxygen wouldn't reach in the pulmonary blood, wouldn't reach that in the alveolar air. So this is again a summary of what we have just mentioned in the previous slides. So at the arteriolar end of the pulmonary capillary, the partial pressure of oxygen is 40, and along the length of the pulmonary capillaries, oxygen diffuses into the blood along its pressure gradient. And oxygen rises and equilibrates to 1.2 millimeters of mercury within the first 1/3 of the pulmonary capillary, or within the first 0.25 of the second. Again, this is the perfusion limited oxygen exchange. So see here, so 0 means the beginning of the pulmonary capillary. 0.25, so now the partial, here this is the blue line is the partial pressure of oxygen. See, the partial pressure of oxygen increases, and it reaches that in the alveolar air after about 0.25 of the second, or after the blood has moved 1/3 of the pulmonary capillaries. So diffusion of oxygen is perfusion limited. So same thing here. Oxygen equilibrates with the first 1/3 of the pulmonary capillary. So by the end of the first 1/3 of the pulmonary capillaries, the partial pressure of oxygen in the blood would be exactly the same as the partial pressure of oxygen in the alveolar air, which is 100 to 105 millimeters of mercury. This is again the normal perfusion limited exchange of oxygen, and this is the abnormal diffusion limited exchange of oxygen. This is the situation when the exchange of oxygen is grossly abnormal. This is abnormal, but this is grossly abnormal. You can see here that the partial pressure of oxygen rises only very slightly. But here, still there is rise in the partial pressure of oxygen. So this is abnormal. This is the situation. So you can see this could represent the exchange of oxygen during strenuous exercise, and this could represent the exchange of oxygen in pathological conditions like emphysema or like fibrosis. B, this is what we have, the picture, same picture like what we have A, but at high altitude. The transport of nitric oxide across the respiratory membrane is also perfusion limited, as we just mentioned in the previous slides. In fact, nitric oxide takes a shorter distance and less time even than oxygen to get equilibrated between the blood in the pulmonary capillaries and the air in the alveoli. So, by only 1/5 of the pulmonary capillary, remember oxygen takes 1/3 of the pulmonary capillaries to get equilibrated. Nitric oxide gets equilibrated within the first 1/5 of the pulmonary capillaries. So we finished with the perfusion limited and the diffusion limited exchange of gases, and now let's describe a very important physiological concept, which is the diffusion capacity. And how can we measure the diffusion capacity for oxygen? This is a very useful pulmonary function test. It assesses the diffusion capacity of the lung. In other words, it indicates how efficiently oxygen diffuses across the alveolar capillary membrane from the alveoli into the blood. It is difficult to measure the diffusion capacity of oxygen directly. So what we do, we measure diffusion capacity for carbon monoxide, then we use this to calculate the diffusion capacity for oxygen. So how do we measure the diffusion capacity for carbon monoxide? The subject starts the test by expiring all the air out of the lungs. So the air which remains now in the lungs is the residual volume. Then the subject inhales a gas mixture that contains small amount of carbon monoxide, approximately 0.3%, and we ask the subject to inspire this mixture of gas till reaching the total lung capacity. Then we ask him to hold his breath for approximately 10 seconds. Then air is exhaled. We ask him to expire the air. The concentration of carbon monoxide in the expired air is measured. Now, the concentration of exhaled carbon monoxide is subtracted from the concentration of inhaled carbon monoxide, and the difference between these two signifies is the volume of carbon monoxide that has diffused across the alveolar capillary membrane. الفرق بين الكمية الفرق بين تركيز كربون دايوكسيد في الهواء، الكربون مونوكسيد في الهواء اللي تنفسه في الهواء اللي خرجه بالزفير. This signifies the volume of carbon monoxide that has diffused. Okay, and we mentioned that all carbon monoxide binds to hemoglobin, So the concentration of carbon monoxide in the plasma is considered to be 0. Thus, the partial pressure of carbon monoxide in the alveolar air is essentially the same as since there is no partial pressure of carbon monoxide in the blood, so the gradient which moves carbon monoxide is the difference between the partial pressure of carbon monoxide in the alveoli minus the partial pressure of carbon monoxide in the blood. But the partial pressure of carbon monoxide in the blood is negligible. So the gradient is the same as the partial pressure of carbon monoxide in the alveoli. Now, this is the equation which we use to measure the diffusion capacity for carbon monoxide. Volume of carbon monoxide that diffuses into the blood, and we know this, divided by the partial pressure of carbon monoxide in the alveoli minus the partial pressure of carbon monoxide in the arterial blood. And we have agreed that this is approximately 0. It's negligible. So we divide by the partial pressure of carbon monoxide in the alveolar air, which we can measure very easily. Now, to calculate the diffusion capacity for oxygen, all what we do is we multiply the diffusion capacity for carbon monoxide by 1.23. So this diffusion capacity is a very important pulmonary function test. So it assesses the efficiency by which oxygen diffuses across the alveolar capillary membrane. So we can have things which increase the diffusion capacity for oxygen, and we can have things which increase the diffusion capacity for oxygen. We are worried about the things or the causes of the decreased diffusion capacity for oxygen. For example, destruction of the alveoli, because this decreases the surface area of the respiratory membrane, and this decreases the diffusion coefficient. Remember Fick's law. If the respiratory membrane is thickened, again remember Fick's law, this increases the diffusion distance, so this decreases the diffusion capacity, and this also decreases the diffusion coefficient. In alveolar edema, because now there is fluid in the alveoli, this also increases the diffusion distance and decreases the diffusion coefficient. And when perfusion is decreased, or when there is anemia, because the level of hemoglobin is decreased. Remember these causes from the Fick's law of diffusion, which we described early on during the lecture. Things which increase the diffusion capacity for oxygen include increased perfusion, or when there is polycythemia, the opposite of anemia, when the level of hemoglobin increases and the more hemoglobin is available to bind oxygen. Okay, so in interstitial lung diseases, here when we have the disease in the interstitial of lung, when there is fibrosis in the lung, when the respiratory membrane is thickened, when there is thickening of the respiratory membrane or the exchange membrane, the diffusion of oxygen is now diffusion limited and not perfusion limited. So we will have an increase in the gradient in the partial pressures of oxygen in the alveolar air and in the arterial blood. Remember, under normal conditions where the exchange of oxygen is perfusion limited, there is no gradient in the partial pressure of oxygen between the alveolar air and the arterial blood. So this is what we have here now. Now oxygen diffuses in interstitial lung disease. Oxygen diffuses slowly due to the loss and the damage of the alveoli, and it doesn't get equilibrated with the alveolar air. So even by the end of the pulmonary capillaries, the partial pressure of oxygen is still less than the partial pressure of oxygen in the alveolar air. Finally, it is very important to keep the alveoli dry. Dry means that there is no fluid. There is only a very thin fluid layer with the surfactant here that lines the alveoli. But the remaining of the alveoli is filled with air. And we need to prevent fluid from entering and accumulating into the alveoli. So the alveoli should be kept dry, and alveolar edema should be prevented. So now let's see what are the forces which influence fluid accumulation in the alveoli. For example, the hydrostatic pressure within the pulmonary capillaries. This is a force that favors the movement of fluid into the alveoli. The colloid osmotic pressure within the pulmonary capillaries has an opposite action. So this is a force that favors the movement of water into the capillaries, out of the alveoli. The surface tension, this is the surface tension force. No, this is a force that favors movement of fluid into the alveoli. The alveolar pressure, PA, this is a force which helps to prevent the movement of fluid into the alveoli. So these two forces, the hydrostatic pressure of the blood within the pulmonary capillaries and the surface tension, these favors the movement of fluid into the alveoli. And these two forces, the air pressure in the alveoli and the osmotic colloid pressure, they help to prevent the accumulation of fluid in the alveoli, so they prevent alveolar edema. So in order to keep the alveoli dry, we need to limit the hydrostatic pressure within the pulmonary capillaries, and we need to maintain the colloid osmotic pressure. We need to limit the surface tension, and that's why we have the surfactant, and we need to maintain an adequate pressure inside the alveoli.